All right, hello everybody. Some announcements, nothing new, just a reminder that Chapter 7, Part 1, Achieve, is due Monday at 9. This goes up to the section with the ideal gas law, which we will get through today and a little bit more. So yeah, you'll have everything you need to complete that. Our unit exam 2 is next Friday, so a week from today, covers chapters 5, 6, and 7. Chapter 7 up to what we're covering in class today. And it will have some multiple choice questions, some short answer questions, and then your chapter 5 and 6 learning curves are available and due next Sunday, so in 9 days. At the end of class on Wednesday, we went through this problem, and I didn't initially have this number. I forgot what it was, 1.8 or something, but the correct answer is 2.20 atmospheres. So you just want to make sure you have that in your notes. And okay, so this section we covered that combined gas law, the top right corner, that the pressure and volume and temperature of a gas at initial conditions can be related to those values and final conditions through this equation. And then our next law is Avogadro's law, and this relates the volume of a gas to the amount of gas present. So in Avogadro's law, this states that the volume of a gas is directly proportional to the amount of the gas. So if we have fixed pressure and temperature, if you increase the amount of the gas, you're increasing the volume. I think this is quite intuitive if you think about filling up a balloon from, for example, a helium tank. You connect the helium tank to the balloon, helium gas exits the tank and enters the balloon. So here we're focused on the volume of the balloon. If you add more gas to the balloon, the volume of the balloon will increase. So increasing amount of the gas will increase the volume of that gas. And they're directly proportional, so if you double the total amount of the gas, then you're doubling the volume. If you take 1/3 of the amount, then you have 1/3 of the volume. And with that, we'll right away go to some iClicker questions. So this one's not on your slides. But if we have a gas at a certain pressure and temperature, those are remaining constant. The gas occupies 20 liters. And let's say half of the gas sample escapes. What's that final volume? This is more of a conceptual question. We don't have a bunch of values to work out an equation. So if we think about we're losing half the gas, then what happens to the volume? And then you have 2 questions that are being pushed to your devices. The second one is the learning check that's in your slides.
I didn't read it.
So 1 more minute. So you need two enumerators. You can't do anything. You would be, and then your N2 would be on the side. So you put them down here. And then you divide it. There's a lot of or if you want to plug your gas first, and then you use the multiply N2 and divide. So then you divide.
Oh, we had like So, yeah, we're very good at it. We're very good at it. What's the GPA of your building? We had our top, in order to get top 10.
Give you a few more.
We know what it is.
We had to take the majority of the last 10 meetings.
Yeah, you had to take all the APC code and get straight to sentence.
What if he chooses lanes? That's unbelievable.
That's what I got.
So like, I was perspective, like,
Okay, I'll close in 10 seconds here. All right. Okay, so with this question here, we have an amount of gas in 20 liters. We have the amount of the gas in that occupies that volume. Amount of gas, moles of gas, and volume are directly proportional. So if we are taking away half of the amount of gas in moles, we are reducing the volume by half. So if we start with 20 liters, then we'll end with 10 liters. And then for our next question, we're working with some actual values. So we have a sample of 0.329 moles. And in our equation, the N here is moles, the amount of the gas in moles. So we have 0.329 moles of oxygen occupying a volume of 0.944. More oxygen is added. We're not changing temperature or pressure. So we get to a final volume of 2.47 liters, and we're looking for the final amount of moles. So we have initial amount is 0.329 moles. Initial volume is 0.944 liters. Final amount of moles is what we're looking for. Final volume is 2.47 liters. So we will, of course, use V1 over N1 equals V2 over N2. Now we're looking for N2, so we need to rearrange this equation to have N2 in the numerator, it's currently in the denominator, and by itself on one side of the equation. So first, to get N2 as a numerator, we need to multiply both sides by N2. That will cancel it out on the right. So we get N2 times V1 over N1 equals V2. And then we need to simplify, well, not simplify, but divide and multiply to get N2 by itself in this numerator. So we need to multiply both sides by N1. So then we'll have V2 times N1. And then we need to divide both sides by V2. So we'll have V2 in the denominator on the right side. So we're multiplying by N1 over V1, multiplying by N1 over V1. So we get N2 equals V2 times N1 over V1. And now we can plug in our values and solve for N2. So V2, 2.47 liters. N1, 0.329 mole. V1, 0.944 liters. So N2 is equal to 0.861 moles.
for the exam, will we have to put like the whole rearranging of the equation, or can we just like say that we recognize that it's like possible?
Yes. So if it's a short answer question, you should show the work that you're doing to rearrange the equation. If when you're working through it, you prefer to start with v1 over n1 equals v2 over n2, plug in values, and then simplify and rearrange, that's fine. You don't have to rearrange the variables first. Either way is fine. Okay, well, we will move on then. When we are talking about the volume of a gas, we are often, I guess maybe not often, but you might see in an equation that temperature and pressure is defined as standard temperature and pressure. So they'll say at standard temperature and pressure, you have X moles of gas, and then some more information. So standard temperature and pressure, that means something to us in science. Standard temperature is defined as 0 degrees Celsius, which is equal to 273.15 Kelvin. So these are equivalent values, just our two different units that we use, Celsius and Kelvin. So if you see a statement that a gas is at standard temperature, that's 0 degrees Celsius or 273.15 Kelvin. And then standard pressure is 1 atm. So our standard atmospheric pressure, this could be also 760 millimeters of mercury. Again, these are equivalent values, just different units. So if you see a question that says a gas at standard temperature and pressure, again, there's 0.5 moles of a gas. Well, then you have information about the mole amount, the temperature of the gas, and the pressure. So you're given a lot of information if all they say is that it is at STP. Now we can also define, in the next slide, the molar volume of a gas. So the molar volume of a gas is measured at STP. That's important that we're at standard temperature and pressure, 0 degrees Celsius and 1 atm. If you have 1 mole of any gas, doesn't matter what the identity of that gas is, that occupies 22.4 liters. So this balloon here, we have 1 mole of helium. That would weigh 4 grams due to the molar mass of helium at 273 Kelvin, so standard temperature, and 1 atm, standard pressure. The volume of this balloon is 22.4 liters. Here, you might be able to see this easier on your slide, but here we have 1 mole of oxygen, which would weigh 32 grams. We're at standard temperature and pressure, so again, 1 mole of oxygen also occupies a volume of 22.4 liters. Here's another example. We have 1 mole of nitrogen, 28 grams, standard temperature, standard pressure. The volume of 1 mole of nitrogen is 22.4 liters. So it doesn't matter what type of gas you have, as long as you have 1 mole of that gas at standard temperature, at standard pressure, and its volume is 22.4 liters. This next slide states all of that. So the volume of 1 mole of any gas at STP is 22.4 liters. It doesn't matter the identity of the gas, so it doesn't matter if you have helium, oxygen, nitrogen, argon, any gas. The molar mass of the gas also doesn't matter. Now this might come up, I actually don't think it will, but there is a corollary. If you have equal volumes of any gas, those would contain the same number of particles as long as temperature and pressure are the same. If that does come up, we will call it out. So you might imagine molar volume. This can be helpful if we're working in stoichiometry. Like maybe we have some volume of oxygen gases reacted at standard temperature and pressure. Well, you can use that 1 mole of the oxygen gas is equal to 22.4 liters to convert from volume to moles. I'm sure we'll see examples of that in the future. Any questions so far before we go to our next section? Okay, well, next section is the ideal gas law. So this relates pressure, volume, amount of gas, and temperature. So the volume of the gas, if we think about all of the other laws that we've learned so far, volume of a gas is proportional to the amount of gas, so that's N. It's proportional to temperature, T, and it's inversely proportional to pressure. So if you increase amount of moles, if you increase N, you're increasing volume. If you increase T, temperature, you're increasing volume. If you increase pressure, then you're decreasing the volume. So this relationship can be converted to an equation by adding what we call the universal gas constant. And that is R. We will define R on the next slide. But if you imagine multiplying both sides by P, then we have P, pressure times volume, is proportional to amount times temperature. Here we have pressure times volume is equal to amount times temperature times this gas constant. So this gas constant takes into account that proportionality, and we can set those two values equal to each other. So this equation, it is provided for you on the equation sheet for exams, but this is a good one to remember for your future lives in science. That PV equals nRT for an ideal gas. And so R, the universal gas constant, the value is reported right here, 0.0821, and its units are liters times atmosphere divided by Kelvin times mole. So volume times pressure divided by temperature times amount. R is also equal to, please write this down, this will be used in the future. If we change, well, you might remember, liters times atmosphere can be converted to a joule. So the universal gas constant converting liters times atmospheres to a joule is 8.3145 joules per Kelvin times mole. In the future, not today, but later sections in this chapter, we will talk about gases doing work, the energies of gases, and so using the universal gas constant in units of joules is helpful in those equations. But for today, we'll use that first value, 0.0821, liters times atmosphere divided by Kelvin times mole. And if we're using the universal gas constant, we're using this equation, that means our pressure has to be in units of atmosphere, our volume has to be in units of liters, our temperature has to be in units of Kelvin, and then our amount has to be in units of mole. So some conversions may be needed in some questions to make sure you're working with those units. So let's do another practice. This will be another iClicker, so let me get this started. We have 0.04 moles of a sample of carbon dioxide. It exerts a pressure of 1.14 atmospheres, and it's at 25 degrees Celsius. We are looking for volume. So we have amount in moles, we have pressure in atmospheres, and we have temperature. It is in Celsius, but you'll need to convert to Kelvin. We always use Kelvin for gas problems. And we're looking for volume. So pressure, looking for volume. We have amount, we have temperature. We'll use PV equals nRT. And so you are solving for volume. When you submit your answer, use 3 sig figs. So I'll give you all a few minutes and then. Okay, one more minute, let me know. Okay, last call for any responses. All right, we're just reading through the equation or through the problem statement. We're first given 0.0400 moles. That's our N value. So 0.0400 moles. Our P value is 1.14 ATM. Our temperature is 25 degrees Celsius. We need to convert to Kelvin, so we add 273.15. So 298.15 Kelvin. We are calculating volume, so some value in liters for volume. Now we need to use our gas constant. For this question, we're looking for volume in liters, and we have the pressure in units of atmosphere. So we use the R value that incorporates those two units, volume in liters and pressure in atmospheres. So we will use 0.0821 liters times atmosphere divided by mole times Kelvin. So all four of those in this ratio here, liters times atmosphere divided by mole times Kelvin, this is the units for R. So that way, when we solve for volume, we will end with units of liters. Now we have PV equals nRT. We're looking for just volume. We divide both sides by pressure. So volume equals moles times gas constant times temperature divided by pressure. So this is 0.0400 moles times 0.0821 liters times atmosphere divided by mole times Kelvin times our temperature, 298.15 Kelvin, divided by pressure, 1.14 ATM. So just thinking about units, we have in the gas constant, liters in the numerator, atmosphere in the numerator. Atmosphere is canceled out with atmosphere in the denominator. And then in the units, we have mole and Kelvin in the denominator. And we're multiplying by a mole. So units of mole gets canceled out. We're multiplying by Kelvin, so Kelvin also gets canceled out. So then the only unit we're left over with is liter, and that's what we're looking for the volume. So the value here, if you simplify the fraction, is 0.859 liters. And then again, we can make sure this makes sense. Actually, no, we can't. Never mind, it's not a comparison. But this is, so this is our volume of this gas at a certain temperature, certain amount of moles, and pressure. So when we're working with ideal gases, this is the ideal gas law, there are some assumptions that are implicit in assuming that something is an ideal gas. These are stated on this next slide. So the first is that the volume occupied by the molecules in an ideal gas is negligible compared with the volume of its container. So if you think about some container of gas that occupies a volume, most of that volume is empty space, but there are little gas, tiny particles that are taking up some of that volume. But in the ideal gas law assumptions, we assume that that amount of space that's taken up by the gas atoms is so small compared to the size of the container that we assume it's zero. So the only volume that's taken up is that really that empty space. We also assume that the energies generated by forces among ideal gas molecules are again negligible compared with molecular kinetic energies. Molecular kinetic energy is related to temperature, so we're assuming that temperature is a good approximation of the energy that's generated by these gases. In reality, gas particles can have a force of attraction or repulsion towards each other, but we're completely ignoring that when we're talking about ideal gases. So according to this model, a substance will be an ideal gas when its molecules are small and do not attract. Do not attract one another strongly. So small molecules with minimal forces of attraction to each other act more so like an ideal gas. The larger gas molecules act less like an ideal gas, more, I guess the ideal gas assumptions don't align with our large gas molecules or gases that have strong forces of attraction between the molecules. So the further we go away from these properties, the less ideal that gas acts or behaves. Okay. Now we're going to talk about a little bit more about pressure, and we've talked about gas components or containers of gas that have one gas present. So in Dalton's law of partial pressure, we're talking about containers that have multiple different gases. So a gas mixture, in a gas mixture, so if you have a balloon that has helium and oxygen present, for example, we would say that both of those gases and all of the molecules are acting independently in an ideal gas. So gas behavior depends on the number of gas molecules, but not on the identity. So it doesn't matter if you have helium, oxygen, nitrogen, etc. So here's a particle representation to show. We have an empty container. We're filling it up with some helium gas. Helium gas is initially added. Helium gas disperses and occupies the volume of the container. They are floating around. They're colliding with the inner walls. They're colliding with each other. Really, they're taking up that entire space. Then if we take that same tank and add oxygen gas to it, oxygen gas will initially be filtered in through the top, and then it will occupy the space of the container, collide with other molecules, collide with the inner walls of the container. The helium and oxygen are mixed together, but we can assume that oxygen is acting independently of the helium being present. So the oxygen is still taking up the full volume of the container. The helium is still taking up the full volume of the container as well. So the volume of the oxygen gas is equal to the volume of the helium gas. But the pressure that the oxygen gas contributes might not be equal to the pressure of the helium gas. They will have their independent pressures, and then total pressure is the sum of the pressure from the individual gas components. So that's what we have on this next slide. This is Dalton's law of partial pressure. So again, we say we have helium in a container. There's enough helium to have a pressure of 2 atmospheres. We have another container of the same size that has argon. It has enough argon molecules at that temperature to have a pressure of 4 atmospheres. Now, if you take the same amount of helium that contributes to 2 atmospheres of pressure, same amount of argon that contributes to 4 atmospheres of pressure, at the same temperature, same total volume, then the total pressure of them together is the sum of these individual pressures. So 2 ATMs from helium, 4 ATMs from argon, a total of 6 ATM when we combine the two. So here we have this law stated out. Partial pressure is the pressure that would be present in a gas container if one gas were present by itself. So that's the partial pressure, the pressure of just the one gas. And so the total pressure in the container is the sum of those partial pressures. So P total is equal to first gas pressure, partial pressure, plus the second gas's partial pressure, and if there's more, third gas, and so on, until you accounted for all of the gases present. So in that last example, we would say helium had a pressure of 2 atmospheres, argon had a pressure of 4, and so the total pressure was 6. We got another example on this next slide, oxygen and helium. So we have 3 liters of a gas at 273 Kelvin. We have 4 moles of oxygen, its pressure would be 30 ATM. We have 3 liters at 273 Kelvin with 8 moles of helium, its pressure is 60 ATM. Then we have 3 liters at the same temperature, so same volume, same temperature. Now we have 12 moles of gas. We've added the 4 moles of oxygen and the 8 moles of helium. Then the total pressure is the sum of those individual pressures. Pressures of oxygen plus pressure of helium gives us a total pressure of 90 atmospheres in this mixture. A little bit more about total pressure, and then we'll do a learning check. So the pressure exerted by an ideal gas mixture is determined by the total number of moles. So if you know total number of moles in the mixture, then you know total pressure. Well, we can express the total number of moles as the sum of the moles of the individual gases. So total number of moles is moles of helium plus moles of oxygen. So we substitute total moles for this equation here, so add the helium plus oxygen into pressure equals moles times gas constant times temperature over volume. Then we have the pressure of helium is equal to the moles of helium times gas constant times temperature times divided by volume. Pressure of oxygen is moles of oxygen times RT divided by V. So this equation here, or this part of the equation, moles of helium times gas constant temperature divided by volume. This is the pressure of helium. And then the second part is the pressure of oxygen. So total pressure in this example is the pressure of helium plus pressure of oxygen. This is Dalton's law of partial pressure. Okay, now let's put all of this into a problem here. We have a 4.5 liter flask holding 2 gases at 298 Kelvin. The partial pressure of gas A is 1.4 atmospheres. The partial pressure of gas B is 3.6. And then we're now adding 4.3 moles of a third gas. We're not changing temperature, we're not changing volume. And then we're looking for the total pressure. So let's dissect what we have so far here. We have, initially they give us the volume. So we have our volume is equal to 4.5 liters. They are also giving us temperature. So temperature is 298 Kelvin. They give us the partial pressure of gas A. So we'll say pressure for subscript A is 1.4 atmospheres. We have partial pressure of the second gas, gas B. We have 3.6 atmospheres. We're looking for total pressure. But we're adding a third gas. But we don't know the pressure of that gas. We only know moles. So we know moles of gas. We'll say this is gas C. So moles of gas C is 4.3 moles. We're looking for total pressure, which would be the pressure of gas A plus the pressure of gas B plus the pressure of gas C. So let's write that out. PA plus PB plus PC. We know pressure of gas A, we know pressure of gas B. We need to find pressure of gas C. So we're looking for pressure. We have moles of gas C. We have the total volume. We have the temperature. So we can use PV equals nRT to solve for pressure of gas C. So if we're using the moles of C, then we'll get the pressure for gas C. And then we can add that together. So we can use PV equals nRT, but we're looking for just pressure of gas C. So we use moles of gas C, then volume, gas constant, and temperature stay the same for all gases. So pressure of gas C is equal to moles of gas C times R times T divided by volume. So now we're just plugging in values. 4.3 moles of gas C, R 0.0821 liters times atmosphere divided by mole times Kelvin. Temperature 298 Kelvin divided by volume 4.5 liters. So again, in the numerator, we're canceling out Kelvin, we're canceling out mole, we will cancel out liters, and we're left with ATM, our pressure unit. I calculated 23, pressure of gas C is 23.38 ATM. Yeah. Yes, so the other R value has units of joules per mole times Kelvin. And having the units of joules doesn't help us when we are using liters for volume and atmosphere for pressure. So later in the chapter, we'll do some equations where we're talking about the energies of gases, and in those questions, we'll use the other R value. Okay, so we found the pressure of C, but that's not the total pressure. We need to add all of these together. So just continue this down here. Pressure of gas A, 1.4 ATM. So total pressure is pressure of gas A plus pressure of gas B, 3.6 ATM, plus pressure of gas C, 23.38 ATM. So all of this together is 28. That's not the correct sig figs, but it's 28 ATM. No, it is the correct sig figs because this is 2. We have 2 sig figs here, 2 sig figs here, so that would be 23. So 28 ATM. Yeah, like this should be, we're not rounding till the very end, but this would be 2 sig figs. So it would end at the 23. So then when we add it together, we can only keep this place here. So nothing past the decimal. Oops. Yeah. It's because, yeah, it's because the 23. Oops. Thank you.